It's another example with 4 polynomials. Okay, here they are. That's the first one. That's the second one. That's my third one. And the fourth one is like this. Again, we try to address the same question, whether this set of 4 polynomials is linear dependent or independent. And again, the approach is entirely identical to what you saw before. We start off with the definition of linear dependence. We spell out this linear combination and raise the question whether this is 0, whether this can be made 0, while not every coefficient is 0. If you drop this last clause, then of course we can make it into 0. We just choose over every coefficient 0, but we don't care about such making. We care about the one where we can make it a 0, even though not every coefficient on the left-hand side is 0. If you can manage to do so, then the system is linear dependent. So I do the same step as before. I just replace all of the p's with actual polynomials on the right-hand side. This is the one. This is the substitute for P1. This is a substitute for P2. This is a substitute for P3, and that's the last substitute for P4. Again, as before, we expect this to be true for any R. That's exactly the nature of this relation. It's true for any X because what you can see here from functional perspective, it's a function on the left-hand side, function of X, it's a function of X on the right-hand side. And we approach this as if these functions are equal identically, so they're equal for every X. We rearrange as before. We collect all of the free terms, lambda 1, 2, lambda 2, lambda 3. No free term here, that's the free term. All of the X terms, all of them here. 2 of them from 2 lambda 1 from here. No lambda 2, 1 lambda 3, and 3 lambda 4. That's the X term. The square term, none of them from here. 1 lambda 2 from here. 4 lambda 3, and 3 lambda 4. This is a typo, it's supposed to be 4 here. Just fix this quickly. Oh, wrong. It's a typo, but I fixed it in the wrong place. I'm supposed to fix it here. Lambda 4, and this one is missing x cubed actually. Yes. So the cubic term 1 lambda 1 from here. 3 of them from here, that's fine. No cubic in lambda 3 and negative 2 in lambda 4. Everything is fine now. And again, now we engage the same property. We have a polynomial where we clearly identified every coefficient. And we have this polynomial identically 0. At this stage, we engage this property of polynomials from the first year and say this only happens when every individual coefficient is 0. And now I just frame this as a system of linear equations. This step is always present when you do this when you do linear dependence independence with polynomials. This property of polynomials you engage to make a transition from this relation after you finish the rearrangement into the system. And again, you're looking at the system, the question still stands whether we can come up with the non-zero solution such that it will work in the system, and the answer to that will be inspection of the row echelon form. So we extract the augmented matrix again, left-hand side, right-hand side. I just copy all of the coefficients. I take this to the row echelon form. And let's just look. The answer will come from the shape of the row echelon form again. This is a row echelon form, and what we can spot here, we can spot that the last column on the left-hand side is not leading column, right? It doesn't have a pivot, which suggests non-zero solution. We can even come up with that solution if you do a full parametrization or a partial parametrization. This slide doesn't do it, but we can actually do it together. So look at this. If I need to come up with a solution to this, I need to solve, I have to do back substitution. And I will do it in an express version of that, so with no parameter, but I will choose something which is non-zero. So I'll do it here probably. So if I do that, it will be lambda. So I choose for the unknown, the one which corresponds to a non-leading column, something, well, often when we parameterize, we use a parameter for that. But in this case, we don't really care for the complete solution, right? We only need one non-zero solution, so we don't care for the entire solution. That's why you can use this shortcut, express version of back substitution. You don't parameterize, but you just set to a numerical value of your choosing. Anyone will do, except 0, of course, because if you choose 0, the rest of the unknowns will be 0 as well. So often the frequent choice is just 1. Sometimes you can choose something else to avoid dealing with fractions, but in this case 1 will do, I think. So you choose what? You choose lambda 4, and then you solve for the rest of the leading column. So lambda 3 will be coming from the from the third row, and that will be -1, right? I'll do it here because it's a -15, 15. If you move this 15 on the other side, if you do your back substitution in full, I gave you plenty of examples where it was done in full. So I hope you know what's happening right now, because a lot of manipulations, when I do back substitution right now, I do it implicitly in my head, just by looking at the row echelon form. If you struggle with this, you have to revisit the very first section we started off with, systems of linear equations. So my lambda 2 will be, again, from the second row, that will solve into -4. That's a cancellation of this -4, and then inside that will give me -3 lambda 4 plus lambda 3, for which I know the values of those two. The values are -1 for lambda 3, and so it will be -4. The result will be 1. That's the value for lambda 2 after back substitution. And now lambda 1, I solve it from the first line. The result will be -2 lambda 2, -lambda 3. And those values I know already. It's 1, -2, and +1, so it's a -1. These are the numbers, these are the coefficients which will work here and will convert the left-hand side into 0. It's not the only set of numbers which will do this, but we just need one. So what I'm saying, actually, if I now do this actual combination, if I combine, look at this, -1, -p1 plus p2, -p3, and plus p4, result will be 0. That's the combination we found. You don't have to find these coefficients all the time. I mean, if the question just says determine or decide whether your set is dependent or independent, you can just do so by looking at the row echelon form. But if the question insists on coefficients, then you have to do this extra step, doing this back substitution and producing these coefficients. Another point which I'd like to make here is this. If you've done this a lot in the first year, you probably develop a habit of just scrapping all of these intermediate steps and jumping by looking at this and jumping right in here into the metrics. This happens a lot. In the first year, it's relatively, I mean, they treat this relatively tolerable. The only problem is often people make mistakes, like a 50-50 chance you will make that mistake unless you remember that the connection between original polynomials and the system. The mistake is that you arrange the coefficients in rows rather than columns. If you make that mistake, that's a clear evidence you don't understand this process. Because the coefficients, they go into columns, not into rows.